When you hear the word tsunami, what comes to mind? For most of us, it's a massive earthquake, a violent rupture of the seafloor that heaves the entire ocean upwards. And while that is the most common cause, it's far from the only one. The ocean has other, more secret ways of unleashing its fury. Tsunamis can be born from the silent collapse of an underwater mountain, the explosive meeting of fire and water, or even from the very air above the waves. These are the Aseismic tsunamis, waves without a quake. Today, we're diving deep into the unseen origins of the ocean's power, exploring the silent, but no less deadly, maritime threats that challenge our understanding of the planet. Let's start with one of the most powerful and hidden sources, a submarine landslide. Imagine a huge section of the seafloor, miles wide and hundreds of feet thick, suddenly giving way and sliding down a slope. This can happen for a few reasons. Sometimes, layers of soft clay deep in the sediment act like a slippery banana peel, or rapid buildup of sediment, say from a large river delta, can trap water inside the layers, creating high pressure that makes the whole slope unstable. Often, a small earthquake, one not big enough to cause a tsunami on its own, provides the final jolt that sets the whole mass in motion. Once it starts moving, this colossal slab of rock and mud acts like a giant paddle. It pushes water ahead of it, creating a wave crest, and leaves a depression behind it, creating a trough. The faster the landslide accelerates, the more energy it pumps into the water, and the bigger the initial wave. In some cases, the landslide starts above water, a coastal cliff, or a mountainside collapsing into the sea. This creates an enormous splash, generating a terrifyingly large local tsunami. A key thing to understand about landslide tsunamis is that they are masters of local destruction. Unlike earthquake tsunamis that can cross entire oceans, landslide waves have shorter wavelengths. This means their energy spreads out and weakens more quickly over long distances. So while they might not threaten a continent thousands of miles away, for any coastlines nearby, they are an absolute nightmare, arriving within minutes, with almost no warning. History is filled with chilling examples. Take Lituya Bay, Alaska in 1958. A magnitude 7.8 earthquake on a nearby fault triggered a massive rockfall. 90 million tons of rock and ice fell from a mountainside and plunged into a narrow inlet. The result was the tallest wave ever recorded. The water surged up the opposite hillside to a mind-boggling height of 524 meters, or 1,720 feet. It scraped the slope clean of every tree, every patch of soil, leaving behind bare rock. It was a stark lesson in the power of an impact-generated tsunami in a confined space. But perhaps the most important case study for scientists happened in Papua New Guinea in 1998. A magnitude 7.0 earthquake struck offshore. Based on the quake's size and type, experts didn't expect a major tsunami. But about 20 minutes later, three enormous waves, some up to 15 meters high, crashed ashore, tragically killing over 2,200 people. Scientists were baffled. It took intensive surveys of the seafloor to find the real culprit. Using sound waves to map the seabed, they discovered a huge underwater slump, a landslide that had been triggered by the earthquake. This event was a wake-up call. It proved that submarine landslides weren't a minor threat. They could be catastrophically deadly, and we desperately needed to start mapping these offshore hazards. And these events can be even bigger. Off the coast of Norway lies the scar of the Storegga slide, a prehistoric mega landslide from about 8,200 years ago. It involved an almost unimaginable 2,400 cubic kilometers of sediment. The resulting tsunami was so large, it left a distinct layer of sand and debris across the North Atlantic, hitting the coasts of Norway, Scotland, and even Greenland, with waves estimated to be up to 20 meters high. By studying these ancient deposits, we get a glimpse of the terrifying potential of the world's largest unstable slopes. Next, we turn to another source of immense power: volcanoes. When fire meets water, the results can be explosive and tsunamigenic. Volcanoes can generate waves in several ways, and they account for a huge number of all volcano-related deaths. One of the most common ways is a flank collapse. Volcanic islands are often just unstable piles of lava and loose rock. Weakened by hot fluids from within, or just by the constant pull of gravity, a whole side of the volcano can simply break off and slide into the sea. This is exactly what happened on December 22, 2018, at the Anak Krakatau volcano in Indonesia. After a period of eruption, the volcano's entire southwestern flank collapsed into the Sunda Strait. Critically, this collapse didn't create a large earthquake signal, so the traditional tsunami warning systems remained silent. Just 30 minutes later, waves slammed into the coasts of Java and Sumatra, killing over 430 people. It was a tragic, modern reminder of this specific danger. This has also led to intense debate about volcanoes like Cumbre Vieja in the Canary Islands, where scientists have identified a potentially unstable flank that, in a worst-case scenario, could trigger a tsunami across the Atlantic. Another mechanism is when a volcano unleashes a pyroclastic flow. These are superheated, fast-moving avalanches of ash, rock, and gas. When these flows pour from a coastal volcano directly into the ocean, they displace huge amounts of water, generating a powerful tsunami. But the most powerful volcanic tsunamis are often tied to a caldera collapse. This happens when a volcano violently empties its magma chamber, causing the entire structure above it to collapse into the void. This sudden subsidence of the seafloor displaces a colossal volume of water. The most famous example is, of course, the 1883 eruption of Krakatoa, also in Indonesia. A series of gigantic explosions, coupled with the collapse of two-thirds of the island into a new caldera, generated waves up to 40 meters high. They completely wiped out 165 coastal villages and killed an estimated 36,000 people. Sometimes, modern science can even change our understanding of ancient history. For centuries, the massive tsunami that devastated the Minoan civilization around 1600 BCE was blamed on the caldera collapse of the Santorini volcano. But recent marine geophysical research suggests the caldera was actually closed off from the sea when it collapsed. The new theory is that the main tsunami was actually generated by massive pyroclastic flows from the eruption pouring into the sea. It shows how our ability to probe the past is constantly evolving. And finally, volcanoes have even more exotic methods. A powerful underwater explosion can directly create waves. And as we saw spectacularly in 2022 with the Hungatonga Hunga Hapai eruption, a massive explosion can create a pressure wave in the atmosphere that travels around the world. As this atmospheric wave moved over the ocean, it pushed down on the water, generating a true global tsunami that was measured in the Pacific, the Atlantic, and even the Caribbean, demonstrating a bizarre, planet-spanning connection between the sky and the sea. This brings us to our third and most unusual category of aseismic tsunami: waves from the sky, known as meteotsunamis. These are tsunami-like waves, generated not by geology, but by weather. The process starts with a fast-moving weather system, like a squall line or a group of thunderstorms, that causes a rapid drop in atmospheric pressure over the ocean. This pressure drop lifts the sea surface by a few centimeters, creating a long wave. Normally, this wave would be tiny and harmless. But under the right conditions, a special kind of amplification called Proudman resonance can occur. This happens when the speed of the weather system perfectly matches the speed of the ocean wave it's creating. When they are in sync, the storm continuously feeds energy into the wave, causing it to grow larger and larger as it travels across the continental shelf. As this amplified wave approaches the coast, it can be magnified even further. If the wave's period, the time between its crests, matches the natural rocking period of a harbor or a bay, it can create a sloshing effect, like water in a bathtub. This is called harbor resonance, and it can amplify the wave to destructive and even deadly heights. Meteotsunamis happen all over the world and even have local names. They're called Risaga in Spain, Siga in Croatia, and Abiki in Japan's Nagasaki Bay. They're surprisingly common, even in places like the Great Lakes. While most are small, they can be dangerous. In 1954, a meteotsunami in Chicago swept 7 people from piers to their deaths. In 1979, an abiki in Nagasaki Bay reached 5 meters high, causing 3 fatalities. They are a sneaky, localized hazard that are often completely underestimated. So how do we see these unseen threats? Marine geophysics gives us a powerful toolkit. Techniques like multi-beam bathymetry use sound to create high-resolution 3D maps of the seafloor, revealing the telltale scars of past landslides. Seismic reflection profiling lets us see beneath the seafloor to identify the weak layers that might fail in the future. For real-time detection, we have instruments like ocean bottom pressure sensors, which sit on the seabed and can detect the passage of a tsunami wave just centimeters high. And today, we can even use GPS satellites. Remarkably, a tsunami wave creates a subtle ripple that travels all the way up to the ionosphere. By detecting this atmospheric disturbance with GPS signals, we can actually see the tsunami from space, sometimes offering a faster warning than the wave itself can provide. The world of aseismic tsunamis shows us that the ocean's dangers are more complex than we often assume. From silent underwater collapses to fiery volcanic explosions and freak weather events, destructive waves can be born from a host of sources that don't shake the ground. The future of tsunami safety depends on an integrated approach, one that uses every tool we have, from the bottom of the ocean to the satellites in the sky, to watch for all the varied triggers of the ocean's fury. Understanding these hidden forces is the only way we can truly protect our coastal communities from their might.